Hi. This is AI hardware software code design breakout session. I'm really glad that we have a great layout for this afternoon's session. First of all, we'll have a tech talk session hosted by Rita, Gupta, and the second session is a panel discussion hosted by Brian. And I'll just have a short intro about the two hosts. Ms. Rita Gupta, she's a principal system and hardware architect at the Sony Cloud Gaming R&D. And she holds various technical roles in the SoC architect, design, performance in different organizations. And for the second session, Brian is going to be the moderator. And Brian is the director of memory storage application pathfinding at Microns. And he searches for opportunities to combine compute, memory, interconnect, and the software for performance and efficiency, mainly for Micron's future product. And Brian has 30 years experience at Oracle, RDBMS, virtual operating system, and focusing on this basically the performance for the database. And he is also the active member for computational memory system and the AI hardware software co-design, and also ML proof storage working group. Thank you. So welcome, Rita, for the first session.
Thank you. Let's see. About a year ago, an explosion happened in the tech world when generative AI models such as ChatGPT, Stable Diffusion, DALL-E, and Midjourney were released to all of us. These models are cool. They can be used for fun, or they can be used for work. However, at the end of the day, they require an enormous amount of compute power to do anything that we as users perceive to be useful. These systems are brutally expensive. Today, as a part of this tech talk session presented by the OCP AI hardware software workgroup, we are going to go over the challenges which are posed by these generative AI models above and beyond our traditional models. In order to appreciate the challenges better, I would like to start off with some of the properties of these models. So let's start by understanding what are the differences between the two models. The traditional AI models are trained on a set of data which may be labeled or unlabeled. And as a result of training, some rules are generated, which are later on used in the inference phase for predictions. Generative AI models, on the other hand, are trained on a vast amount of data, such as text, data from the Wikipedia, from the internet, images. As a part of training, the model tries to learn the context and retains the context, just as we humans do, and it's able to generate new information during the inference phase. To understand the challenges that are posed by these models, let's try to look at some of the trends which are posed by these AI models. We'll start with the compute trends for AI ML training. As per the reference on the slide, if you look from the beginning of the time of the ML journey, maybe from like the 1950s or so, we can classify the age into 3 eras. The first is the pre-deep learning stage, which started around the 1950s all the way until the early last decade. During this time, the models double every 2 years, which coincides with Moore's law. The computational capabilities reached about a teraflops. The second stage, which is the deep learning stage, started around early last decade, around 2010. It's still continuing today. The models have been doubling at a much faster rate, which is about once every 6 months. That's about 4x the Moore's law, and the compute capabilities have reached about an exaflop. And lastly, which is our large-scale era, which is the age of the LLMs, which started around 2016. They basically double every 10 months, so the doubling has slowed down a bit, and the compute capabilities have gone to a zeta flop. So as you can see, the total compute capabilities that is required for training these models has gone up from a teraflop to a zeta-flop in a period of about a decade. So what kind of challenges does this put on us? We actually need some kind of a flexible compute infrastructure for this. The innovation that needs to happen here is we need to choose what kind of compute we want. Do we want GPUs? Do we want CPUs? Do we want domain-specific accelerators? Or do we want FPGAs? And this is a problem that we need to solve as a part of this open source community. The second trend that I would like to look at is the parameter size trend. Parameters are the configuration variables that are learned during the training phase. And if you look at the trend line here from 2018 to 2023, GPT-1 had about 100 million parameters, and GPT-4 has about 1 trillion parameters. Over a period of 5 years, the total number of parameter size has gone up by almost 10,000x. So what are the challenges to these plays? These parameters need to be stored in memory and storage, so we need higher and higher capacities. We need to access these at a much faster rates. The parameters also need to be transported to and fro from the memory to the compute and vice versa. And this implies a stressed interconnect or a challenge for us to come up with more innovative interconnect architectures. The next trend that I would like to look at is the data size trend. Data size, the data set is really required to train the model. For the LLMs, these are tokens. Tokens have different definitions. They can be characters, they can be word, they can be text, subtext, or a lot of information. If we look at the trend from 2018, about 1 billion tokens were employed for LLMs, to 2023, where around 1 trillion tokens are required to train these LLMs. And this corresponds to a 1,000x increase in the last 5 years from 2018 to 2023. What are the challenges to these plays? So this data needs to be prepared, ingested, and archived. This affects the storage architecture for our infrastructure. The model training requires high throughput and low latency. And that typically affects pretty much everything from compute, memory, storage, and interconnect. And these are the problems that we need to solve. These models are so large that they no longer fit on a single node or even like a couple of closely knit multi-node systems. To do that, these models need to be distributed all across the infrastructure. The typical parallelisms that have been used for distributed parallel training are, 1, data parallelism, which basically helps with faster training. The second is model parallelism, which helps with loading larger models. And there are some newer techniques in between, like the pipeline parallelism. Earlier, inference with traditional AI models used to be considered as pretty inexpensive and could be done on a single CPU node or a single GPU node. However, once we go to large LLMs, the inference has different constraints. So for the first token generation from any of the models, say ChatGPT, latency matters a lot. And for subsequent token generation, it's the throughput that matters. And hence, distributed inference across multiple nodes is emerging trend for LLMs. Both distributed training and inference ends up with different kind of communication patterns within the nodes, such as all gather, all reduce, et cetera. So what are the challenges that this poses on our infrastructure? First is just the general connectivity or the interconnect architecture between the compute, the memory, and the storage. The second is we do need to distribute these workloads across the different infrastructure components. And for that, we require some kind of a software ecosystem, which consists of innovative schedulers and compilers, which can be used to distribute these workloads over our disaggregated infrastructure. So I just went over a couple of properties of the LLM models. And beyond this, there is one thing that has always been a sticking point or a problem for any of the hardware systems. And this is something that is the memory wall. There has always been an orders of magnitude difference between the performance of compute and the performance of memory. And this is something that has existed from the 1980s, and this performance between the processor memory is continuing to increase. And this, again, poses a similar kind of problems that we just discussed before. One, we do need to move our tokens and parameters, which are stored into the memory, to be supplied to compute just in time. The LLMs are posing an extremely high memory bandwidth requirements of the order of terabytes per second or petabytes per second, along with the requirements for lower latency. And this is pointing towards a new shift or a new paradigm for our memory scalability. So hopefully, the preview that I just gave helps you to understand the challenges that is posed by these newer models much better. And we have a bunch of speakers from both industry and academia who are going to deep dive into all of these topics so that you can better appreciate these challenges and hopefully understand the problems that we need to solve as an open source community. The topics that would be presented by subsequent speakers are, the first one would be on compute infrastructure co-design, which would be presented by Pepe. This will be followed by challenges on scale up and scale out for a disaggregated infrastructure. That would be presented by CMAC. After this, Danny and Taksang would be presenting memory scalability. Isaiah would be talking about storage scalability, as well as showing some of the customer use cases that they are seeing at Weka.io. And finally, Tushar would be presenting modeling methodology and tools for hardware-software co-design. So we had another speaker, Srinivas, who couldn't make it due to some of the work commitments. So Tushar would be the only speaker who would be presenting on his behalf as well. And with that, let me invite Pepe, who is the assistant professor at the EC department at University of Pittsburgh, to go over her talk.